Swayam Prabha. Digital India. Educated India.
Okay, so the second trick, welcome back everyone. The second trick is that whenever a body is cut out into a number of parts, the body is cut out into a number of parts making equal contribution to the moment of inertia, then the moment of inertia formula for each part is the same. The moment of inertia of each part is the same as that of the whole body, Okay. So, which means that the mass of the body can be replaced. Basically, all we have to do is to replace the mass of the body with the mass of the part, right? With the mass of the body replaced with the mass of the part. Okay. So that is what we have. So in just to give you an example, the moment of inertia of the whole sphere, of the whole or the solid sphere, we are talking about a solid sphere, is 2 by 5 ma square, which is the moment of inertia of a solid hemisphere. Solid hemisphere, the moment of inertia is the same of the whole sphere, is same as that of the solid hemisphere, except that now the mass has to be replaced by m by 2, because hemisphere will have exactly half the mass, right? So the moment of inertia of the solid hemisphere is the same as the moment of inertia as the whole sphere, about the same axis that under consideration. So then the next set of results are a set of two theorems. The first one is the parallel axis and the second one is the perpendicular axis theorem. So the parallel axis theorem says, parallel axis, it says that let Ig be the moment of inertia of the body about some axis passing through the center of mass. So let Ig be the moment of inertia of a body about some axis through the center of mass G, right? So let I be equal to the moment of inertia MOI about the parallel axis, then what we have is that I is I of G plus plus m times a square, where a is the perpendicular distance. It's a perpendicular distance between the two axes, between the two parallel axes. Okay. So we are talking about, let's say, about a given axis. So let's say this is my IG. IG is the axis passing through the center of mass of the object, right? And we want to find, rather than finding the moment of inertia about this axis IG, we want to find it along I. Let's say I, another axis I, which is parallel to IG. then all we have to find is the perpendicular distance of this new axis I from the old axis or the original axis IG, and sum it up, sum the contribution, which is MA square. Okay, so let us look at the proof of this result. The proof. So typically in multivariate calculus we introduce parallel and perpendicular axis theorems, but we never introduce the proof. But this course in SwayamPrabha we get a chance to see the proof of these two theorems. Very vital and very crucial results for our rigid body dynamics. Okay, so let's say that we are given the center of mass of the object. Let's say this is G, and let's say we are given another axis which is our axis I, and let us say the perpendicular distance of this axis I from the center of mass G is A, right? G is where the natural axis is there, IG. And let us now introduce 3 points, one on the axis which is exactly perpendicular to the center of mass, 1 point here on this new axis A, and let's say we introduce let us say the particle under consideration is P, and let us now say that we have the axis under consideration is this new axis IG, old axis IG, and let us keep another point B on this old axis, and then the particle under consideration is P, so let us say that it has a distance R from the center of mass, right? So we have and then we can also add another point C. So for B, A, B and C, which has a position vector, so let me write down R. Let me write down R here, and C here, which is C is this is the point C. Okay, so then let my center of mass axis IG is G comma N. Center of mass IG axis be G comma N and A comma N, right? And this is, so center of mass axes are these, and so what we have is, so G comma N, and then let us say that A comma N is on the parallel axis. So A comma N is on the parallel axis. So N being the direction along the axis, right? So here is the direction N. So that's the direction N that we are talking about. Okay, so that is the direction along the axis. So then let us say that R is the distance of the particle P, from the center of mass. So that is what we have drawn in this diagram, right? So and further, let us denote PB and PC to be the perpendicular axis be the perpendicular to the two axes, perpendiculars to IG and I, right? So PB is this point, so that is perpendicular to this axis, and PC is perpendicular to this axis, right? Are the perpendiculars to IG and I. So then we see that from the diagram we have that PB square is equal to G. So PB square is equal to GP square minus BG square. So that is GP square minus GB square. And we see that this is also equal to R square minus R dot N square. Okay, so then PC square is AP square minus AC square, and we see that this is R minus A square. So PC is R minus A square. So R minus A square. So this is AP square is this. So AP square minus AC square. So AP minus AC. AP minus AC. Right. So that is my CP square or PC square. So that is the case. So R minus A. Okay. So then R minus, AP is R minus A square, and AC is R minus A dot with N. R minus A dot with N whole square. Right? So what we get is that PC square is R square plus A square minus 2RA minus R dot N. Right? So R square plus A square minus 2RA minus R dot N whole square. Right? So what we get is, so what we have is that PB square. So this is just a simple application of triangle rule. We have just opened up this expression, let's say star. So this is from star, right? So then, so this is R square is PB square, right? And plus A square minus 2RA, and so PB square was R square minus R dot N square. So we have used R square minus R dot N whole square. So that is our PB square. So similarly, let me call this expression as 1. And now I'm going to multiply this 1 by M on both sides. So we are multiply 1 by M and sum over all particles. Sum over all particles P. Right? And we see that I is Ig plus summation Mi A square minus 2 times summation Mi Ri, summation Mi Ri dot A. Right? So all we have done is multiply by M and sum over all particles that is under consideration. Okay. So we see that PC square when multiplied by M, so that is the moment of inertia about the new axis. So that's PC square. And Ig, PB square is Ig. So PB square is the, when you multiply by M, you are multiplying by the perpendicular distance square times M. So that's the moment of inertia about the center of mass axis. And then the rest of these are the new terms. Notice that Ri dot A, so then this is Ig plus M. So summation Mi is M, Ma square minus 2 times A dot M times R. Right? So this quantity summation Mi Ri is nothing but we can multiply by divide by Mi, summation Mi, and multiply by Mi. Right? So we have that. This is the case. Okay. So so we see that this is M times the center of mass. So the center of mass, we can always keep the center of mass to be the origin. Without loss of generality, we can shift our origin to the center of mass, and in that case R becomes 0 and this whole term vanishes. This whole term vanishes. Right? And what we get is that I is nothing but Ig plus Ma square, and that is what the parallel axis theorem is. Okay, so then let's look at a quick example with an application of this. So a uniform a uniform rectangular plate of mass m and sides 2a and 2b, the problem says find the moment of inertia about a side of length 2a. Find the moment of inertia of about a side of length 2a. So for the rectangular plate, we already know that the moment of inertia about its natural perpendicular axis is 1/3 m times half the length along that perpendicular length, right? So that is from the stick result or from the rod result, right? So we have used the trick one where we have squashed the plate into a rod. So what I just said is, let me write it. So it's already known that the moment of inertia of the plate about the x-axis is 1/3 mb square, right? So we are talking about a plate. So what we have is, let's say this dimension is b and this dimension is a, and so the moment of inertia about this this axis is 1/3 mb square, and we see that so that's the result which is already known. And then we want to find the moment of inertia about the side 2a, about the length 2a. So this is length 2a. So what do we do? We hold on. So we want to find the moment of inertia about a side of length 2a. So we want to find the moment of inertia about one of the sides of this plate. So the new axis of rotation is at a distance small a, right? So all we have to do is, using parallel axis theorem, let me call this new axis as I. So I is nothing but the old moment of inertia plus m times the perpendicular distance, which is ma square, and that's about, this is the length. Sorry, what is given is find the moment of inertia of the side of length 2a. So if this is our side 2a, so this is 2b. So this particular distance is b, half of the side. So this has to be mb square. So what we get as a final result is 4/3 mb square, right? Okay, so that, I think, with this small example, the idea of applying parallel axis theorem is quite clear. The next is the case of perpendicular axis theorem. The perpendicular axis theorem. So what we have is, suppose a lamina has a point O in its plane. A lamina has a point O in its plane, and let O, X, Y, Z be a set of Cartesian axis, right? With OX and OY in the plane of the lamina, and OZ is the perpendicular, right? So the problem says that in this case, the moment of inertia of the three perpendicular axes, are related as follows. Related as OZ is equal to OX plus OY. So basically it says that, suppose you have an object and it has an axis of rotation which is given by this this OX axis. So OX, so let's say IOX, and similarly along the Y axis we have another axis of rotation IOY. Then we have the third axis which is IOZ, which is going to be which is the perpendicular axis perpendicular to the object of the plane of the object. Then this is what the relation between the three axes of rotation is, right? So the proof of this result is relatively simple. So suppose let's say we have a typical lamina with mass m and coordinate xy, coordinate of the coordinate xy of the lamina, xy comma 0. We're talking in 3D. So let P be a typical point on a lamina. Typical point on a lamina, with mass m and coordinate x comma y comma 0, right? Then the perpendicular distance of P from OX, OY, OZ are given by Px given by y, Py given by x, and Pz given by x square plus y square. Okay, so these are my distances of this point, this sample point on the lamina, right? So then we can clearly see that Pz square is equal to Px square plus Py square, right? And if we multiply this Pz square, Px square and Py square with the mass of the point object at P, let's say we multiply by let's say mass of the point object P, and we immediately see that the result follows, right? So mass by P and sum over all P, sum over all point objects P. We multiply by mass MP and sum over all point objects P. So we see that that is what we have, right? Okay. So which means that OZ is equal to OX plus OY. Okay, so then let us see an application of this perpendicular axis theorem. So the application that I have in mind is that of a uniform rectangular plate. So a uniform plate, rectangular plate, has mass m and sides 2a and 2b, right? We find the moment of inertia about the axis through its center. Find the moment of inertia of the axis through its center perpendicular to its plane, right? Find the moment of inertia about an axis passing through its center and perpendicular to its plane. So we know that, again, if we draw the plane, if we draw this plate, this has sides 2a and sides 2b, and we see that the moment of inertia is we can quickly see we can have two imaginary axes, one parallel to the x-axis, one parallel to the y-axis, and we can quickly find that the respective moment of inertia about the x-axis will be half mb square, b being the perpendicular distance from the axis to the sides of the rectangle, right, plate, and OY will be half MA square, right? So this is for each of the sides. We can use the same as trick 1 to find the relation between the moment of inertia of the plate and the rod, right? And that those are the same. And then using perpendicular axis theorem, the final answer is half MA square plus half MB square, right? So that is what we have, that OZ is this. So well, so that is for the plate. How about for a disc? So moment of inertia of a uniform circular disc of mass m, radius a, and about a diameter. So we have to find this new moment of inertia of a disc about a diameter. So we have to, so here is the disc, and we can take any diameter of the disc. Let's say the diameter is along the x-axis, so this is the moment of inertia OX, and this is the moment of inertia about OY. So we need to find, we know that from the symmetry OX is equal to OY, so we need to find this, right? But we know that along the perpendicular axis OZ, the moment of inertia of the disc is half MA square, A being the radius of the disc. So which means that this is also equal to OX plus OY by perpendicular axis theorem, and we get the final answer that about the diameter of the disc, the moment of inertia is 1/4 MA square, right? Okay, so that is what we have. So then I think with these two results, I am quite ready to discuss our angular momentum principle to begin with in 2 dimensions. So what have we got? So we are talking about the angular momentum principle to begin with in 2D. Okay, so the problems, to begin the discussion, let us at least first highlight what are the key concepts we will be touching upon. The key concepts are conservation of angular momentum, a rigid body motion, conservation of angular momentum, rigid body motion. So these are the two major things. Okay, so then the definition, we are talking about moment of force and torque. Okay, so suppose a force F acts on a particle. So we are talking about the concept of torque. So suppose the force F acts on a particle P with position R relative to the origin O, right? And then the moment of force F, about O is defined to be, the moment of force about the point O is defined to be KO is R cross F, where R is going to be the perpendicular distance of the axis of rotation and the point object where on which the external force is acted upon, right? So so that's my moment acting on the particle. So then let me call this as 1. So then for a system of particles, particles P1, P2, Pn with position vectors for a system of particles with position vector r1, r2, rn, we see that they are acted upon by forces F1, F2, Fn and respectively, right? So let us say that this is the case. So the total moment the total moment are going to be K0 is Ri cross Fi. So we sum it over all particles under consideration. So Ri cross Fi. Remember, this is a vector cross product. So now, in order to reduce the variables, we can take, without loss of generality, we can take one of the position vectors to be the origin of the system. That will reduce our variables or our degrees of freedom by at least 1. In 3D, it reduces by 3, and so on. So without loss of generality, we can take any point as origin. Any point, any position vector of the particle as origin, and then the moment, let's say about A. In that case, let's say the point taken as origin is A, right? So in that case, we see that Ka is summation Ri minus. So let us say this position vector of this point A is small a. So in that case, now my new moment taking the position vector of the point A as the origin, my new moment will be Ri minus A, because now all the other position vectors have to be subtracted from the position vector of A. So Ri minus A cross Fi, right? Automatically the contribution of point A is gone. And then this is nothing but, again, we can distribute this cross product. We see that this is K0 minus A cross F, right? So what we have is, that is what we have. Okay, so then the geometric interpretation is that, so so that's what we have. So then we can quickly, for a system of particles, we can quickly say that, so let us quickly wrap up this module by just giving the geometric interpretation of what we have just written. So the geometric interpretation is that K0 is F times R cos alpha n hat plus whatever is on the right hand side, right? So what it means is that we have that O. Let us try and discuss this geometric interpretation. So that's a separate point of discussion in this problem. So we are going to discuss this in the next module. So thank you so far for listening. So thanks a lot.